Hello everyone, welcome you all to Life System 9 of NPTEL course Fluid Flow Operations taught by Professor Shubhita Kumar Majumdar. And my name is Nagfani Sai Kumar. I am the teaching assistant for this course. So last week we have discussed about drag and lift along with cavitation as well. So this week we'll be studying about dimensional analysis and also law of similarity and significant dimensionless numbers. Okay, so the first part, that is dimensional analysis, will include homogeneity of dimensions. It also includes Rayleigh method and also Buckingham pi method for dimensional analysis. Homogeneity of dimensions, Rayleigh method, and Buckingham pi method. Okay. So first, let's look at the first topic, that is dimensionless analysis. Then we'll go on to the subsequent topics. So we know that the modern engineering is becoming complex because of the complex flow behavior is being accounted, and this cannot be often addressed by purely theoretical investigation. Okay, so purely theoretical investigation fails to yield a practical and workable solution because of the complex nature of the fluid behavior. So that is why we have to deal with dimensional analysis. Okay, so dimensional analysis deals with a method for reducing the complexity of a physical phenomena to a simplest form and also most economical form prior to obtaining a quantitative solution. So principles of dimensionless analysis and also dynamic similarity are extremely useful in the use and interpretation of the experimental data. Okay. First thing that we'll encounter in modern engineering is complex flow behavior, and this cannot be solved using the conventional methods which we use, that is pure theoretical investigations. So we will not be getting any solution for this. Okay. So that is why we'll have to go with something called dimensional analysis, which will reduce the complexity of the flow behavior or reduce the complexity of a problem that we are dealing with. Dimensional analysis. So it basically reduces the complexity of the problem. So there's a scientist by the name Bridgman in 1969. So he explained that the principle of dimensionless analysis is to deduce from a study of dimensions of the variables in any physical system certain limitations on the form of any possible relations between those variables. And this method is of great generality and mathematical simplicity. So this was his statement. Let me write it down. The principal use of dimensional analysis is to deduce from a study of the dimension of the variables in any physical system, certain limitations on the form of any possible relationship between those variables. And the method of a great, the method is of great generality and mathematical simplicity. Okay. So sometimes experiment cannot be possible to carry out on the full size of scale. Okay. So let's say when water is flowing in a dam, like you want to investigate the effect of water flow on a dam or on a particular channel or hydraulic missions. Okay, so that won't be possible in, you cannot carry out experiment in large scale. Okay, for the sake of economy and convenience, it is required that you have to produce small scales or you have to produce a replica of small replica for test purpose. Okay, so certain laws of similarity must be followed in order to ensure that the test model, that is a smaller pilot model or test model, can be applied to the prototype. So in order to apply these laws of similarity, one has to express the experimental results in terms of non-dimensionless numbers. Okay, so this norm dimensionless analysis and dynamic similarities are useful in finding such non-dimensional factors. Okay, so you can take many examples. So where you cannot directly go for the actual large scale equipment, let's say be it hydraulic blades or steam turbines. So before they before being tested in actual scenario, so you have to first develop the replica or the prototype of the steam turbines and hydraulic blades, because so whenever you're testing these blades in an actual scenario, or let's take you need, let's say, the blade of hydraulic or let's say the steam blade of steam turbine. Let's say this is having a length of around 5 meters, for example, arbitrarily, let's say 5 meters. So, and its fabrication involves some, you have to spend some money to fabricate this material, right? So, let's say if there's something wrong in the design or you have to modify something, so this entire fabrication cost will be wasted, right? So, that is why we cannot directly test on the actual scenario. So, whenever you have to spend too much amount or more amount of money on the actual scenario, so instead of directly going for such bigger size or a full size unit, you will be developing the replica, which is of a smaller size, but will be an exact replica of that full size unit. Okay, so you will be doing tests on these smaller units, and then you'll be applying the results on the full size units. So these results, when you perform the experiments on the smaller prototype, okay, when you perform the experiments on the small prototype, Okay, let's say this is like 5 centimeters, for example. Okay, so the actual size is having 5 meter length, and the prototype might be having 5 centimeter length arbitrarily. So once you get results from this prototype or test unit, so these results are converted to work the machines with water or steam, or let's say these results are then converted into full scale or applied to the full scale equipments. Okay. So this is possible by applying certain laws of similarity with the help of dimensional analysis. So we'll also look at the laws of similarity. So there will be two types of similarities. One is kinematic similarity and the other is dynamic similarity. We'll look at that as well. Okay, in a while. So this is the importance of dimensionless analysis. So let's look at the other uses of dimensional analysis. So it is basically a branch of mathematics which deals with dimensions of quantities. It is a branch of mathematics which deals with dimensions quantities. And this dimensional analysis, it is very useful to find whether an equation of any flow phenomena is rational or not. Okay. So generally dimensional homogeneity equation is called a rational equation. So this will be helpful in identifying if the equation is a rational equation or not. So useful to find whether an equation of any flow phenomena is rational or not. Okay. So generally dimensionally homogeneous equations are called rational equations. Dimensionally homogeneous equations are called rational equations. Okay. So coming to the next use of dimensional analysis. So by dimensional analysis, the relationship between various physical quantities in an equation can be obtained easily. Relationship between various physical quantities in an equation can be obtained. And coming to the next use of dimensional analysis. So rational formula for a flow phenomenon can be derived. Okay. And also it helps in making suitable smaller size models in which experiments can be performed to predict the performance of the actual prototypes. So that is one of the major use of dimensional analysis. So because of this, we'll be able to save lot of time, energy, and also money that we are spending on the actual prototypes. It helps in making suitable smaller sized models in which experiments can be performed to predict the performance of the prototypes. This is one of the major use of dimensional analysis. Okay. So let's look at fundamental and derived quantities. There are something called fundamental and derived quantities. Okay. So to assess or measure an unknown quantity, we must have an acceptable unit, right? So let's say you want to measure weight of a body, or you need to have an acceptable unit. So be it kg, be it gram or microgram, whatever it is, you need a unit to measure the quantity, right? So you can also measure time. So you need either seconds or hours. So for any quantity, if you have to measure a quantity, you need an acceptable unit. Okay, so there are many different standard units, and so you can either choose. So for it depends on the convenience that for a particular quantity. Let's say you want to measure weight of rice bag. So we'll not be measuring weight of a rice bag. Let's say in our households we'll be using a 25 kg rice bag, right? For example. So we might be using 25 kg rice bag. So is it convenient to express that in terms of kg or in grams? It will be convenient to express in terms of kg, right? Let's say you want to express the number of or the time that we have in an entire day. So we can either express it as 24 hours, okay, or you can also say 24 into 60 minutes, okay, or this can also be 24 into 60 into 60 seconds, right? So which would be the convenient way? So even if you simplify this, what will be the number of minutes that we'll be having in a day? You just multiply it and tell me number of hours that we'll be having in a day. Sorry, number of minutes that we'll be having in a day. Just multiply the equation. So multiply these numbers. It will be 1440 minutes. And what will be the number of seconds that we'll be having in a day? 86400, right? 86,400 seconds. So which would be the convenient way to express the number of the time that we have in a day? 24 hours will be a convenient way, right? So even though we have many different units, and we also have different standard units, but the unit that we are choosing depends upon the convenience, okay, to measure that particular quantity. So out of all these units, out of all these quantities, there are a small number of basic quantities that are to be expressed as standard quantities, and they may be expressed in terms of basic units. So these basic quantities are called fundamental quantities, which are only three in number. Fundamental quantities, and the three fundamental quantities are mass, length, and time. And how do we express these terms? So M indicates mass, L indicates length, and T indicates time. Okay. So all other quantities such as area, volume, velocity, acceleration, force, pressure, surface tension, all these quantities can be expressed in terms of these fundamental quantities, and those quantities are called derived quantities. Can be expressed in terms of fundamental quantities. So examples, there are many quantities like all the other like area, volume, pressure, force, all the quantities like they are basically derived quantities. So you can obtain these derived quantities either by multiplying or dividing the fundamental quantities that are that is mass, length, and time. So you can either multiply them, divide them, add them, and from there you can get these derived quantities. And in the derived quantities, we again have two different types. The first one is primary fundamental quantities, and the second one is auxiliary fundamental unit. And then we also have something called convenient fundamental units. So we'll come to that. Primary, auxiliary, and convenient fundamental units. First one is primary fundamental unit. Okay. So these are nothing but length, mass, and time. Okay. And coming to auxiliary fundamental units. So measurement of certain physical quantities like physical quantities in electrical, thermal, illumination, and elementary particles, disciplines, are represented by the fundamental quantities, and these quantities are used only when the particular classes are involved. So, be it ampere, which basically used to express the current amount of current, and we have Kelvin, which is basically used to measure the temperature. Then we have candela, moles. Okay, so all these are considered as auxiliary fundamental units, which can only be used in those particular cases. Okay, so we can these auxiliary fundamental units include ampere. We have Kelvin, which is given by K, candela, and mole. Okay. And then we have convenient fundamental units. Okay. So for convenience, some engineers prefer to use quantities which is easier to measure instead of say mass as a fundamental unit. So this could be force. So because of just for the sake of simplicity, some engineers will be using force as a fundamental unit. So if you are considering force as a fundamental unit, then instead of using MLT system, you will be using FLT. Okay. So let's look at some important quantities with dimensions. So we have First, let's look at first. Let me write down the fundamental units. So for length, it is what is the unit for length? It is meter, and we represent this by L. Okay, and then for time, we have second as a SI unit. This is SI unit, and then we have mass. So kg is SI unit, and then we have temperature. Kelvin is the SI unit, and then we have current. Ampere is the SI unit, and number of elementary particles. Number of elementary particles. SI unit will be mole, and luminous intensity. SI unit would be candela. That is CD. So let's see how we can express derived quantities in terms of fundamental units. So let's consider area. So area is length into breadth, or basically distance into distance, right? So we can express this as L square. And then we have volume. Volume is length into breadth into height for a cuboid. So it will be basically L cube. Then let's say velocity. So velocity is nothing but what are the units of velocity? Meter square per, sorry, meter per second, right? So this would translate into L by T if you express in terms of fundamental units. So you have to express it as L into T power minus 1. L power T minus 1. Then we have force. Force is nothing but mass into acceleration, right? What are the units for mass? Kg. And for acceleration is meter per second square. So if you change this into dimensional, if you write this in terms of fundamental units, it will be m l power t power minus 2. So this will become m l t power minus 2. So this is how we'll be able to express different derived quantities in terms of fundamental units. And then we have kinematic viscosity, we have dynamic viscosity, and we have density, surface tension, so bulk modulus. All these quantities you can express in terms of dimensional units. So let me just write it down directly. So for viscosity, is dynamic viscosity, it will be m L power minus 1 T power minus 1, and for kinematic viscosity, it will be m L sorry, L power 2 T power minus 1, and for density, it will be m L power minus 3. Okay, so this is how we will be able to express different quantities, different derived quantities in terms of dimensional units. Okay, so in order to carry out this dimensional analysis, we have two different methods. One is Rayleigh method, and the other one is Buckingham pi method. Buckingham's pi method. So What are the differences or so coming to Rayleigh method, this method is based on the fundamental principles of dimension homogeneity of physical variables. Let me write it down parallelly. So it is based on fundamental principle of dimensional homogeneity of physical variables. And Buckingham by method, it relies on the identification of variables involved in the process. So further, a few of these have to be marked as repeating variables, okay, depending upon the system that you are considering. So it relies on the identification of variables involved in a process. And sometimes there might be a repetition of the repetition of variables. So some that is why you have to mark them as repeating variables. And the Rayleigh method, the dependent variable is identified and expressed as a product of all the independent variables raised to an unknown integer exponent. Dependent variables or dependent variable is identified and expressed as a product of independent variables raised to the raised to an unknown integer exponent. And Buckingham method, the repeating variables among themselves should not form a non-dimensional number. Okay, so that is one rule for a Buckingham method. So the repeating variables among themselves should not form a non-dimensional number. So coming back to Rayleigh method, equating the indices of n fundamental dimensions of variables involve n independent equations. So if there are n number of fundamental dimensions, then we'll be getting n number of equations. And on the other side, Buckingham method, if a physical process has n variables and from these j are repeating variables, then we'll be having n minus j independent non-dimensional numbers that can describe the process. The physical process has n variables, and from these, out of these n variables, let's say if j are repeating variables, so then there are n minus j independent non-dimensional numbers that can be that can describe a process. Okay. So again, on coming back to Rayleigh method, these n equations are solved to obtain the dimensional groups. Okay. So both Buckingham method and Rayleigh method of dimension analysis determine only the relevant independent dimensionless parameters of a problem, but not the exact relationship between them. So you have to. So these methods cannot be used to determine the exact relationship, but they can be used to identify the relevant independent dimensionless parameters. So first, let's see how we'll be able to use Rayleigh method. Then we'll go on to the Buckingham Pi method. So there are several steps in this. First step is, so note all the independent variables that are likely to influence the dependent variable. Note all the independent variables that are likely to influence the dependent variables. Step 2. So step 2 is, if y is a variable that depends upon independent variables, say x1, x2, x3, then a functional equation can be written as, if y is a variable that is a dependent variable, let's say this is a dependent variable, and x1, x2, x3 let's say so on till xn. These are independent variables. So then we can write functional equation as y is function of x1, x2 till xn. Okay. So then coming to step 3. So write the functional equation in the form of y is equal to some c into x raised power a into x2 raised power b, x3 raised to power c till xn raised to power of m. So where is c is a dimensionless constant. Dimensionless constant, and a, b, c are arbitrary exponents. So instead of writing in terms of function, so let's replace this function with some constant, and also let's raise these powers to some arbitrary exponents a, b, c. Okay. So then comes step 4. Express each of the quantities in the equation in fundamental dimensions in which the solution is required. Okay, this is step 4. So now coming to step 5. So by using dimensional homogeneity, obtain a set of simultaneous equations involving exponents a, b, c till m. Simultaneous equations involving the exponents a, b, c till m. Okay. So now coming to step 6. So solve these equations to obtain the values of exponents a, b, c. Step 6 is to solve these equations to obtain the value of exponents. That is a, b, c till m. So now step 7 is to format the dimensional groups by the variables with like exponents. Formation of dimensionless groups by the variables with like exponents. Okay, so we'll take an example and like let's try to understand how to apply this thing. Okay, so let's consider frictional resistance F when a fluid. I'll directly write the question. Let us consider frictional resistance F when a liquid is flowing through a pipe depends on the viscosity, density, velocity of the flow, diameter of the pipe, and pipe surface roughness. So derive a rational equation for pipe flow in terms of dimensional groups by Rayleigh equation. So first step is to identify the independent variables. So what are the independent variables in this problem? Viscosity is an independent variable, density is an independent variable, velocity of the flow is an independent variable, diameter of the pipe is an independent variable, and pipe roughness is also independent variable. Okay. And what is a dependent variable? Force, right? Frictional force is a dependent variable. Okay. Now comes step two. So first we have to express all these quantities in terms of a functional equation. So F for this force is a function of viscosity, density, velocity, diameter, and surface roughness. So now we have to express them in terms of a equation, right? So F is equal to C, some constant into F is equal to some constant into viscosity raised to the power A, density raised to the power B, velocity raised to the power C, diameter raised to the power D, and roughness raised to the power E. Okay. So let's say this equation number, this is 1 and this is 2. Okay. So now we have to write them in terms of dimensional, fundamental dimensions. So step 4 is to write them in terms of dimensional numbers. So how do you express force? Force is ml t power minus 2, right? So this will become ml t power minus 2 is equal to c is a constant, dimensionless constant, so it doesn't have any dimensions. And how do you express viscosity? M L power minus 1 T power minus 1, right? For A into density is ml power minus 3 is kg per meter cube, right? So it will become ml power minus 3 power B into L T power minus 1 into C. So I'm just directly writing down. So velocity is ml T power minus 1, right? And diameter is L for D and roughness is L for E. Okay, so that's the equation number 3. So now we have to equate the like dimensions. So just collect all the terms, all m terms, l terms, and t terms, and then equate the variables on left and right hand side. So then you will be getting simultaneous equations involving A, B, C, D, and E. So for mass, so if you compare all the terms uh, involving mass, then it will be, so on LHS it is 1 is equal to A plus B. This is equation number 4. So here we have mass, here we have mass, and other quantity doesn't have mass, so it will be A plus B. And if you compare L terms, it will be 1 is equal to, so here we have minus A, then we have minus 3B in this equation, so in this term, and then we have C, so it will be plus C, and here we have plus D, and then plus E. So this will be equation number 5. And then if you compare T, you'll be getting minus 2 is equal to minus A minus C. This is equation number 6. Okay. So now comes equation number step number 6. So what is step number 6? We got the equations in terms of A, B, C, D, E, and A, B, C, D, and E. So now we have to solve these equations. So from equation number 4, we can write equation number 4. We can write B as B is equal to 1 minus A, right? This will be equation number 7. And from equation number 6, we can write C is equal to 2 minus A. This will become equation number 8. So, and from equation number 5, we can write D is equal to 1 plus A plus 3B minus C minus C. Okay. So just substitute B and C in this equation. You'll be getting 1 plus A plus 3 into 1 minus A minus 2 minus A minus C. So this becomes 2 minus A minus E. This will be equation number 9. Okay. So now just substitute or try to form dimensionless equations using these relations. That will be step number 7. So we have F is equal to C into mu power A and density into, here it is raised power B, right? So instead of B we can write 1 minus A, right? It will become 1 minus A, and then we have velocity in power. So velocity is raised to the power C, right? So instead of C we can write 2 minus A. This becomes 2 minus A, and D raised to the power D is raised to the power D, right? So instead of D we can write 2 minus A minus E, and epsilon is raised to the power E. Okay. So we have eliminated B, C, and D from the equations or from this equation. So now just collect all the variables which doesn't have A and E. Okay. So it becomes F is equal to C into rho V square into D square, and also collect other variables A and E variables. So it becomes rho V D by mu power minus A, and we also have epsilon by D power E. Okay. So if you just observe carefully, this is a dimensionless group, and this is also a dimensionless group. So just compare the units, just substitute the units, and you'll be finding out that these are dimensionless groups. Okay. Yes or no? Just substitute the units and see if they're dimensionless units or if they're having any dimensions. They are dimensionless. They are dimensionless units, right? Okay. So just take other variables. Take these variables to the other side. you'll be getting F by rho V square into D square is equal to C into rho VD by mu for minus A into epsilon by D for E. Okay, so these are the dimensionless groups. Okay, so you can also express F as F by rho V square D square is equal to function of rho V D by mu and epsilon by D. Okay, so these are will be able to do dimensional analysis using Rayleigh method, and then we come back to the Buckingham pi method. So I guess most of you might be knowing about Buckingham method. Okay, so let's go to the Buckingham method as well. Second, my screen just got froze. Let me just quickly close the tab and then open it. Is the screen visible now? Okay. I think some of the terms, okay, I'll just write it down again. Step 7, we have d power 2 minus a minus e and epsilon power e. And then if you just separate the variables, you'll be getting f by rho v square d square is equal to c into rho v d by mu power minus a into epsilon by d for e. So these are dimensionless groups. So you can also write f by rho v square d square as function of rho v d by mu and epsilon by d. Okay. So coming to Buckingham method, Buckingham's pi method. So Buckingham pi method relies on we have already discussed that it relies on identification of variables involved in the process. Also, few of these variables have to be marked as repeating variables, and the repeating variables among themselves should not be forming a non-dimensional number. And if a physical process has n variables, out of which j are repeating variables, then we'll be having n minus j independent non-dimensional numbers that can describe the process. Okay, this we've already discussed initially. So let's directly go to Buckingham pi method. So according to the theory, the functional relationship among variables x1 and x2 can be expressed as f of x1 comma x2 comma x3 so on xn as 0 n is number of variables, and if j is the number of fundamental units, fundamental dimensions like mass, length, and time, then we have n minus j, right? So the dimensionless groups can be expressed as phi I is equal to x1 to the power ai, x2 to the power bi, so on till xj to the power x j to the power ji and xj plus 1, where x1, x2 till xj are called repeating or core variables, and xj plus 1 are non-repeating variables. So basically, number of repeating variables will be equal to number of fundamental dimensions. So in general, j will be equal to 3. Okay, in general. So generally speaking, j will be equal to 3. Why? Because we only have MLT as the fundamental units, right? So in that case, j will be equal to 3, right? So functional relationship among dimensional groups can be established as pi 2 comma till pi I is equal to 0. Okay, so now comes the steps involved in Buckingham pi method. So step 1 is to identify the relevant variables and functions. And step 2 is to write down the dimensions. Step 3 is to establishment of number of independent dimensions and non-dimensional groups. Step 4 is to choose J dimensionally independent repeating variables. So in most of the cases it will be three. So the first representing the fluid property. Second representing the flow characteristics. And the third representing the geometric characteristics. And also, we should not be choosing density terms like density, gravity, and specific weight as repeating variables. Okay. Coming to step 5, we have to create pies by non-dimensionalizing the remaining variables and by solving the coefficients. Step 5 is to creating the pies by non-dimensionalizing the remaining variables and by solving the coefficients. Step 6 is to setting the non-dimensional relationship. Step 7 is to rearrange if required for convenience. So in this case, you are free to replace any of the pies by a power of that pi or by a product with the other pies, provided retaining the same number of independent dimensionless groups. Rearrange. This is only if required. In this case, we are free to replace any of the pi's by a power of that pi or by a product with the other pi's. So provided it should retain the same number of independent dimensionless groups. Okay, so we'll try to solve the problem. Then it will be a bit clear. So let's take the same example that we have solved just now for using value method. So let's take the same case and try to use Buckingham pi method. So what is the step one? So we have to find relevant variables and functions. So f of f mu rho v d epsilon, all these are the variables and functions. And now coming to step two. So we have to write the dimensions of each and every quantity. So f is ml t power minus 2, mu is ml power minus 1 t power minus 1, density is ml power minus 3, and when velocity is l power t minus 1, then diameter is length, and epsilon is also length. Okay, so now coming to step 3. Okay, so just find out all the relevant variables, number of relevant variables. So we have 6 relevant variables. So n will be equal to 6, and we need to find number of independent dimensions as well. That is j will be equal to 3. So this will be m, l, and t. Okay. So now we have to find out number of non-dimensional groups that can be formed. Number of non-dimensional groups. So it will be n minus j, which is equal to 3. Okay. So now coming to step 4. So what is step 4? Choose j dimensional independent repeating variables. Choose j repeating variables. So it can be, first one is fluid property, right? Which can be represented by using density, and then we have flow characteristic, which can be given by velocity, and then we have geometry, which can be given by diameter. And we have step 5, which is creating pies. That is pi 1 is equal to rho a power 1 v v power b1 d power c1 into f1. Pi 2 is rho power a2 v power b2 d power c2 into mu, and pi 3 will be rho power a3 v power b3 c d power c3 into epsilon. Okay, so now equate the variables. So pi 1 is just have to solve the equations. So pi 1 is rho a power 1 v power b1 d power c1 into f, right? So what are the units of pi? It is unitless. So m power l power 0 t power 0, which will be equal to ml power minus 3 power a1 l power t minus 1 power b1 L into C power 1 M L T power minus 2. So just equate the variables. You will be getting 0 is equal to A1 plus 1, 0 is equal to minus 3 A1 plus B1 plus C1 is equal to 1. And we have one more equation, that is 0 is equal to minus B1 equal minus B1 minus 2. So if we just solve these equations, you will be getting A1 as minus 1, B1 as minus 2, C1 as minus 2. So pi 1 will be F by rho v square into d square. Okay, and similarly if we solve for pi 2 and pi 3, we will be getting pi 2 as mu by d v rho. Okay, and pi 3 will be epsilon by d. You just have to equate them similar to what we have done for pi 1, and then you'll be getting pi 2 and pi 3. So now f of pi 1 comma pi 2 comma pi 3 should be equal to 0, right? So we can also express as pi 1 is equal to f of pi 2 comma pi 3, which basically gives us f by rho v square d square is equal to function mu by rho v d comma epsilon by d. So this is what we got from the same equation, right? From sorry from Buckingham method as sorry Rayleigh method as well, right? So this is how we'll be doing or using Buckingham pi theorem. So, do you have any doubts until now? So, you can apply this to any problem and you'll be able to check the dimensional consistency as well or homogeneity as well. Do you have any doubts until now? Any doubts in the concept that we discussed? Then either unmute yourself and ask me, or you can post them in the chat box as well. Okay. So if you don't have any doubts, I mean we can move on to the other concept. that is similarity. So similitude is a concept applicable to the testing of engineering models. So in order to have complete idea about flow devices, so it is very essential that the model should represent its prototype completely and fully in all aspects. So the similarity between the prototype and its scale model is known as hydraulic similitude. So overall, the conditions that model of a phenomena reproduces all aspects of a behavior of a prototype represented by it are known as conditions of similitude. So what is the difference between a model and a prototype? So generally, similitude is achieved when testing conditions are created such that the test results are applicable for the real design. So the concept of similitude is often used so that measurements made one system in the laboratory environment can be so the measurements that are made from one system in the laboratory environment can be used to describe the behavior of other similar systems in the real world that are outside the laboratory. Okay, so the laboratory built systems are often taught as models, which is a first build of the similar system based on behavior, and its models beyond laboratory frame are called prototypes. So models are laboratory built systems, and prototypes are which are beyond the laboratory scale. Okay. So two systems described by the same physics operating under different set of conditions are said to be physically similar in aspects of certain specified physical quantities. And the ratio of corresponding magnitudes of these quantities between the two systems is the same everywhere. So coming to similarities, we can have different kind of similarities. We can have geometric similarity, we can have kinematic similarity, and we can have dynamical similarities. Okay, so basically in the field of mechanics and hydraulics, models may be classified into these three different types. And a model is said to be completely similar, and a true model with the real application if the model satisfies all the three similarities, that is geometric similarity, kinematic similarity, and a dynamic similarity. So for a multi-parameter model or problem, it is often not possible to achieve full similarity, okay, because of the different complexities uh, or because of the different parameters. So in particular, it is rare to be able to achieve full Reynolds number scaling when other parameters are also involved. Okay, so yeah, geometric similarity, it is, I'll just simply put it in, I'll just put it in simpler words. So I'll not be going into the entire uh, concept. So basically, the model and the prototype should have the same shape, but they'll be in different size proportions, but the ratio of corresponding lengths in the model and prototype will be same. Okay, so let's see how this looks. So let's say we have two cylinders of different lengths and diameters. So let's say this is the first cylinder, and then we have a second cylinder. Or let's say let's draw in the so so let's say this is a laboratory scale, or let's say this is a model, and this is a prototype. Okay, so in this case, all the dimensions, so they can be of different size. They'll be of different same shape, but they can be of different geometric dimensions. Okay, so but there should be a proportionality between. So let's say if this height, let's say this is h and the diameter is d. So for example, so let's say that the height and dimensions of prototype are h and d. So when you're preparing a prototype, so let's say the height of this prototype is say 3h. So the diameter of the prototype should also be 3d because it has to maintain the proportionality relation. So let's say so here what first I'll write the model ratios. So model ratio L1 M by L1 P should be equal to L2 M by L2 P. It should be equal to IR, which is a or let's say this is LR. Okay. So here L1 and L2 are two different or two characteristic physical dimensions, say length and breadth, or it could be height and diameter, okay, something like that. So in this case, M represents model and P represents prototype. So basically, uh, ratio of lengths of one particular characteristic should be equal to the ratio of physical dimensions of the other physical characteristic dimension. So I'll put it in a simpler way. So here, if we take this example, so let's say L1 is height and L2 is diameter. So in this case, height of model by height of prototype, that is 3h, should be equal to diameter of model by diameter of prototype. So let's say this is dp. So maybe this is unknown. Let's say this is unknown. So we know diameter of model, we know height of model, we know height of prototype as well. So as the ratio should be constant, so we can say that diameter of prototype should be 3D. Okay, just to maintain the ratio. Okay, so if this happens, if the ratio is constant, then we can say they are in geometric similarity, like they are having geometric similarity. Okay, and all the included angles should be same in both the cases. So okay, so that is how you'll be able to say if a particular if two objects are in geometric similarity or not. And coming to kinematic similarity, it is a similarity of motion. So the ratios of all corresponding lengths and times, which gives velocity in model and prototype should be equal or same. Okay, so that means both model and its prototype must undergo identical time rates of change of motion. Okay, so basically acceleration ratios, velocity ratios, they should be equal. Okay, so that is how you uh, that is about kinematic viscosity, and then we have dynamical viscosity. So it is basically similarity of forces. So which means both geometric and kinematic similarities are necessary for dynamic similarity. So dynamic similarity can be assumed to exist if ratios of all forces acting on a corresponding fluid particles and boundary surfaces in model and prototype systems are same. Okay, basically Reynolds number should be same in both the cases. Okay, so we also there are also other topics like Reynolds number and also Froude number, Weber number, Mach number, which were discussed in the class. So because of the time constraint, I will not be going through them. So if you have any doubts in those topics, you can ask me, you can unmute yourself or post them in the chat box. I'll try to answer them. If not, we can move on to the problem solving session. If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. Okay, so let's move on to the problem solving session. So coming to first question, force is the dash primary fundamental unit, auxiliary fundamental unit, convenient fundamental unit, none of the above. So it is a convenient fundamental unit, C. So we have already discussed this. Coming to second question, the dimensions of surface tension is m t power minus 2, ml power minus 1, t power minus 1, ml power minus 1, t power minus 2, ml squared, t power minus 2. So what are the dimensions of surface tension? What are the dimensions of surface tension? It will be ml, sorry, m t power minus 2, right? That will be option A. So just write in the formula and then you'll be able to get the dimensions of surface tension. So coming to third question, if there are n variables in dimensionally homogeneous equation and if these variables contain m primary dimensions, then the variables can be grouped into how many non-dimensional groups? So that is n minus m, option B. Coming to fourth question, the dimensions of kinematic viscosity is, again just write down the formula and you'll be able to get the answer. So what will be L square t power minus L power 2 t power minus 1, option B. Okay. So coming to fifth question, in Buckingham's method, the dimensionally independent repeating variables generally represent fluid properties and geometric characteristics. Option B is fluid characteristics. Option C A and B. Option D none of the above. So this also we discussed. So it is geometric characteristics and fluid characteristics. That is option C. Coming to sixth question, Buckingham's method and Rayleigh method of dimension analysis determine only relevant independent dimensional parameters and dash. Option A exact relation between them, B not exact relationship between them, C may or may not be exact, and D none of the above. So it will be giving only relevant dimensional independent dimensionless numbers, but it will not be giving any exact relationship between the parameters, right? So that will be option B. Okay. So coming to seventh question, pressure difference across a soap bubble is related to the radius of the curvature of the soap bubble as option A inversely, option B directly, option C square of the radius of curvature, option D no relation. So what is the relation? It is inversely related, option A. Okay. Coming to eighth question, auxiliary fundamental unit for measurement of magnitude of light illumination is option A radians, option B candela, option C Siemens, option D none of the above. That is candela, CD. Okay. So coming to ninth question, in case of geometric similarity, the model and the prototype should have the same shape but different in size, same ratio of all corresponding lengths but difference in included angles. Option C, A and B. Option D, none of the above. So when two geometries, like when the model and prototype are in geometric similarity, so what should be the case? They should be of same size, sorry, same shape, but they should be having different sizes, right? That is option A. Okay. So coming to 10th question, kinematic similarity is the option A similarity in shape, option B similarity of motion, option C similarity of forces, option D all the above. So it is similarity in motion, that is option B. Okay. And what about dynamic similarity? It is similarity of forces. Okay. So coming to 11th question, the Freud number is the option A ratio of inertia force to viscous force, ratio of inertia force to gravity force, C ratio of inertia force to surface tension force, option D none of the above. So fluid number is ratio of inertia force to gravity force, that is option B. Okay. So if you have any doubts, you can ask me. If not, we can end this session. So if you have any doubts in the problems part or maybe in the theory part, if you have any doubts, you can unmute yourself or post them in the chat box. You can unmute yourself and ask me, or you can also post them in the chat box. I'll try to answer them. If you don't have any doubts, then you can log off. Okay. So if you don't have any doubts, then we can end the session. Thank you, everyone. Thank you for attending the session. Let's meet on next Tuesday.